Okay, everybody. I think I'll start exactly at 11:30. That way you guys will know when I'm going to start, and eventually everyone will be here. So let's start with a little bit of a recap. Okay. So remember what our story is. We have a large network of neurons. Large network full of excitatory neurons and inhibitory neurons. So red for excitatory, green for inhibitory. And in reality, there are typically millions to hundreds of millions of neurons in any one of these networks. These neurons are connected recurrently. And each neuron obeys dynamics that looks like this. So dvi dt equals, let's say, linear integrate and fire. Plus the sum on J. I'm going to write Wij Gj of T. And so this is the leak. Which is about minus 65 millivolts. And so you guys have had biophysics before, but just to be totally clear, since I'm guessing you don't remember everything that you've been told. So Gj of T, remember, is just a little blip. Whatever neuron, so these are spike times on neuron J. On neuron J. And if we looked at memory potential VI, this is VI versus time. So this is minus 65 millivolts. And this is about minus 50. Now this should be kind of review, but the idea is if, let's say, no presynaptic neurons were firing, the neuron would be going like this. If a presynaptic neuron fired, you'd see a little increase and decrease. And this is a PSP, in this case, an ePSP. It's around 0.1 to 0.5 to maybe 1 millivolts. So it's sort of in the 1 millivolt range. This ESP from a single about 1,000 other neurons, or about 1,000 terms in the sum. If one of those neurons spiked and none of the others, you'd see this little blip here. Okay. Now, neurons running around. If it hits about minus 50 millivolts, it spikes, and then so and then it gets reset to about so that's a picture, and then it keeps going again. Okay, for real neurons, there's you got linear integrate for Hodgkin, quadratic integrate, all about the same. Okay, I think I just got kicked off. Appears that you guys are back. Okay, I don't know what happened. Sorry about that.
是我卡了还是？
Okay, you guys, I'm really, really sorry. I don't quite know what's going on. Should be okay now. Internet problems. Okay. Can you guys hear me?
Yes.
Okay, great. I'm really sorry. Don't know what happened. Okay, so here's our picture. I'll be brief. We have a bunch of neurons in here. They're interconnected. And dvi dt equals minus vi minus e leak plus the sum on j wij gj of t. Okay, so current-based model of linear integrated fire neurons. And what we want to understand is, given these equations, what's the behavior of the neurons? And the hard part, of course, are the weights. Okay. And the reason these are hard is because we know that, given the connectivity in our brain, the brain does amazing computations. And we don't really know what the weights are, so we don't really know how the computations are done. So what I've done here is so far considered randomly connected networks. Connected networks. Okay, and when we did that, so really the idea is, it all came down to this. If we have some neuron that gets input, so I've taken one of these neurons and put it out here, it's get some input from excitatory neurons and inhibitory neurons, E for excitatory, I for inhibitory. The defined rate of this neuron, nu I, is some function of not the individual firing rates, but just the average firing rates, nu E and nu I, okay? So this is an assumption. And in a little while, I'll tell you why it's a reasonable assumption. It's valid if for random connectivity. Connectivity. Okay. And once we make this assumption, we can take this network here and reduce it to basically an excitatory population of neurons, inhibitory population of neurons. We reduce it to basically, we reduce a large population to basically 2 neurons. 2 very large excitatory inhibitory neurons, and they interact. Excitation, excitatory neurons excite each other. The inhibitory neurons inhibit themselves, inhibit the excitatory neurons. Okay, and that gives the set of equations, which is tau E, which we kind of made up. And then tau I d nu I dt equals psi I of nu E comma nu I. Okay. Now, psi E and psi I, these gain functions, basically, oops. So these gain functions just tell us the equilibrium value of the firing rates, of the excitatory firing rates given excitatory firing rates. But if they're out of equilibrium, there's dynamics. So if somehow the excitatory firing rate was set too high, so this was positive, excitatory firing rates go up. And this gave us the following picture. So these are nonlinear coupled ODEs, and they gave us the following picture, nu E, nu I, excitatory inhibitory nucleons. Excitatory nucleon looks like this. And inhibitory nucleon, I think I drew it in green, looks like this. Okay. So this is I nucleon. And this is E nucleon. And this point here is about 100 hertz. Okay. And so these are basically equilibria. The nucleons give us equilibria. It says if you set the inhibitory firing rate to this value, the neurons can all be nearly quiet, or they can all be firing at a high rate. And in between is this threshold. Okay, this is an unstable branch. If you just sat here, you get pushed to the right. Here you get pushed to the left. And that gave us, we can actually draw arrows. So these arrows indicate the direction of nu E changing if nu I was fixed. And then there's equivalent arrows for all I nucleons that go like this. And so these really aren't vector fields. The actual vector field looks something like this, right? If you're sitting right here, you're pulled up and to the right. Okay. And the closer you are to this, the less you pull to the right. Over here, you're going to be like this. So these are actual vector fields. And the vectored fields tell you what direction you go and how fast given where you are. And the vector fields, of course, vanish. Oops. They vanish the vector fields vanish right here, okay? So right here, they're really small. So a little bit to the right and down, really small, and then they get bigger over here, okay? So that's a picture in sort of in this abstract firing rate space, and then the corresponding real space picture. This corresponds to in real time. This sort of tells us exactly what's happening. In the time domain, this is time. So we have excitatory firing rate, nu E. It goes up a little bit. It kind of oscillates, and maybe it's damp, maybe not. But what's happening is, what's happening in it is that when excitatory firing rate goes up, inhibitory firing rate also goes up. When inhibitory goes up, that causes excitatory to go down, and this kind of follows along, okay? And that corresponds to a trajectory like this. We just kind of wander around and wander in. And as we saw, that fixed point can either be stable or unstable, okay? So this is, let's label these. So this is nu E, and this is nu I. Okay. Now, one thing that's really important for this is this unstable branch is a big part of this. And the reason there's an unstable branch is that these gain functions are kind of sensitive to firing rates. Okay, so small change in firing rates give a big change in these. And I was actually working that out at the end. So one of the things that we saw that was critical, let's go back to our equation. Equation for voltage. So tau dVi dt. So remember, this is voltage. Equals minus Vi minus E leak plus the sum on J. I'm actually going to put tau V PSP IJ GJ of T. Okay, where GJ of T has this property. So GJ of T jumps up when there's a spike. And we chose GJ of T so that area equals 1. Okay. In fact, to do the analysis, we said GJ of T equals the sum on mu delta of T minus T J mu. So this is time of muth spike on neuron J. Okay, so whenever neuron J spikes, you get this thing. What we did is in the extreme case, we made this thing really tall and steep. Okay, and when we average this quantity, so we took the average of this, what we got is the time average was equal to tau, the sum on J of V PSP IJ nu J. Okay. And that is approximately equal to, tau. So K V bar EPSP nu E minus V bar IPSP nu I. I think I wrote plus the other day. So this is about on the order of 0.5 millivolts. And it's in the order of minus 0.5 millivolts. Okay. And K is number of connections per neuron, average number of connections per neuron equals about 1,000. So each neuron receives an input from about 1,000 others. Okay. And I believe I worked out you can sort of see, go to the next page. You can sort of see why the gain functions are so steep. So we have tau d nu I dt equals minus nu I minus e leak plus, we'll say on average, equals tau k v bar EPSP nu e minus v bar IPSP nu I. Okay. And so this is basically 1,000. So this is a big number, right? The taus cancel, and we get dV/dt is 1,000 times the phi rate. Okay. And I think I worked out. I didn't actually work. You can actually solve this equation. I don't think I did that last time. So if we have tau, let's say excitatory neurons only. Remember the taus. So the taus cancel. So we have dV/dt equals minus vi minus el over tau plus k nu bar EPSP. And this has a solution vi of t minus e leak equals its equilibrium is nu e is k nu bar EPSP. Okay, so that's 1 minus e to minus t over tau. Okay, so this is, if we assume that at time t equals 0, vi equals e leak, it increases like this. Okay. There's actually a tau here. Oh, there's a tau here, yeah. Okay. And what that means is, remember, neuron fires when vi of t minus e leak equals some firing rate, let's say v threshold. And so we have v threshold, this is an e, v threshold equals k tau v bar EPSP nu e 1 minus e to the minus t over tau. If you solve this, you get e to the minus t over tau equals one minus VTH over K tau V bar EPSP nu E. or t equals tau log with a minus sign here, 1 minus VTH over K tau V bar PSP nu E. Okay, which means firing rate nu is 1 over this. I'll go to the next page. So nu, the actual firing rate of our postsynaptic neuron, is 1 over tau over minus log 1 minus, let's go back. Let me get this right. Yep. VTH over K tau V bar PSP nu E. Okay. So this is wrong. Shoot. Oh, I got it upside down. So this is K. I got it right. VTH over K tau V bar PSP nu E. Okay. So the point is, this is about 100 hertz. Tau is 10 milliseconds, so tau equals 10 milliseconds. This is about 100 hertz. That's where that number came from. And let's assume that, we'll assume this is large. So we'll assume this is large. So we can approximate log by log. So this is small. So log 1 minus epsilon is approximately minus epsilon. So this is basically K tau V PSP nu E over VTH. So this number is about 100,000 times 10 milliseconds is equal to 1,000 in seconds. This is times 0.01 equals 10. VPSP, oops, why does that always happen? K tau V EPSP over VTH. So this ratio is about, let's say 1 over 20. Okay, distance to threshold is about 15 milliseconds or so. So basically, this is 100 hertz times, let's say nu E over 2. Okay, so this is very approximate, but this says that when nu E changes by, so delta nu E equals 1 hertz or 1 hertz. So delta nu I equals 50 hertz. Okay, So it's very approximate, but the point is that a small change in firing rate leads to a big change in the small change in average firing rate. So the upshot of this is that small change in average firing rate implies large change in postsynaptic firing rate. Okay, and it really has to do with the fact that the K is large. So a lot of presynaptic neurons, so a small change, 1 hertz change in firing rate has a big effect on the synaptic drive. It has a big effect on this term here, and a big effect on the postsynaptic neuron. So this picture of these nucleins, where this is really this unstable branch, is pretty accurate in large networks of neurons. Okay. So that should have been mainly recap, and all we've done is now made a convincing case nucleins are steep. So the nuclein, just to be clear, so what that means is, so if you plot psi e of nu e, nu I versus nu e, it's going to basically go up here to 100 hertz, and this distance is going to be 2 to 3 to 5 hertz. We say 2 to 5 hertz. So somewhere depending on the properties of the neurons, 1 to 5 hertz. Within 1 to 5 hertz, this can go almost to maximum firing rate. Okay. Okay, so that's the picture we have so far from around the connected networks. I now want to actually take a closer look at why we can talk about average firing rate, and that's going to now that discussion is going to be super critical for understanding structured connectivity. Okay, so I'll go back to our equation. Tau dvi dt equals minus v minus e leak plus the sum on j. I'll say wij e. Let's say wij. Well, wij e nu ej minus wij I. Actually, I use a plus sign nu ij. Okay, so that's a picture we had. And now we want to look more, and effectively what we did in our analysis. So effectively, we let the sum on j of wij e nu ej go to basically number of connections per neurons, w bar e nu e. Okay, so that's really the step that allowed us to say this neuron depends only on the average excitatory firing rate, and then average inhibitory firing rate as well. Okay, so the question what I want to do now is I want to ask, can we justify this step? And it turns out you can if you have a large number of connections. So we're going to drop the E subscript, and we're just going to focus on a simple sum. The sum on J, the K terms in this sum of wij nu j, where wij, all these wij's are positive. Okay? And we're going to write this as, we're going to let wij, because they're all positive, So Wij equals W bar, its average value plus delta Wij. So W bar is 1 over K squared, the sum on Ij, a better handwriting, the sum on Ij of Wij. It's the average value of this weight matrix. And so what that means is delta Wij is 0 on average. So that means this quantity here can be written as a sum on J of W bar plus delta Wij nu J. Okay. We can separate these two terms. The first term is a sum on J of W bar nu J plus the sum on J of delta Wij nu J. The first term is easy. This is equal to K, number of turns in the sum, times W bar times nu bar. Okay. So it's a number, and it's pretty intuitive, right? If all the W's were the same, this is K times the average firing rate. So nu bar, of course, has the definition 1 over K, the sum on J of nu J. Okay, so that's exact. What about the second term? Plus the sum on J of delta Wij nu J. Nu J. How big is that term? So this is a zero mean variable. And it's effectively a random variable. Okay, the weights are chosen randomly. So the Wij are completely random. And so here's something I'm going to tell you that's insanely important, which you sort of have seen probably many times in various ways. If we have the sum on, suppose we have the sum on I, so we'll just give this thing a name. X equals the sum on I of squiggle I equals 1 to K. So squiggle I is a random variable. So the mean value of squiggle I equals 0, and the variance of squiggle I equals, let's say, sigma squared. So sigma I, these are just random variables. Okay, so it could be pulled from a Gaussian distribution. For instance, they can be binary. You could have, they can even do, for instance, so this could be Gaussian. Or you can even have squiggle I equals plus or minus sigma, with probability 1/2. Anything, any random variable you want. So what's the mean value of X? That's the sum I equals 1 to K of the mean value of squiggle I, and that's 0, right? Oh, one more thing, the covariate, these are uncorrelated random variables. Squiggle I, squiggle J equals 0. Okay, uncorrelated. So X is 0 on average. What's its variance? So the variance of X squared equals the sum on Ij, or I prime. Actually, we'll write it like this. The average value of the sum on I of squiggle I squared, right? We're going to write that as the average value of the sum on I of squiggle I times the sum on I prime of squiggle I prime, which we write as a sum on I prime of squiggle I prime. And we can take the averages inside. sum on I and I prime of squiggle I prime. So this is 0 if I is not equal to I prime. That's because the covariance is 0. And it's equal to sigma squared if I equals I prime. So this is just a sum on I equals 1 to k of sigma squared equals k sigma squared. Okay. So the average value of x squared is k sigma squared. So the square root, so the typical size of x sorry, there we go. So typical size of x equals the square root of the average value of x squared equals sigma times the square root of k. Okay. And this is, if you've seen the central limit theorem, you've seen this before. If you have k terms in the sum and there's 0 mean, the sum isn't order k, it's order square root of k. So when I say order, that means how it scales in large k limit. So let's go back now to our equation here. It's the same thing here. This is the sum of k random variables. And I'm going to actually go to the next page and write this down. So we have the sum on j of wij nu j equals k, the average value of the weights times the average value of the firing rates, plus the sum on j of delta wij nu j. Now it's a little more complicated because we have sum on j, but the sum on j we expect, what do we expect? So this should be proportional to the square root of k. It's extremely important. The square root of k is about 1,000. The square root of k is small compared to k. And that's what allows us to ignore fluctuations in firing rates. Okay. But let's actually take a close look at that and see what it is. So this quantity is 0, because these weights are 0 on average, this quantity is 0 on average. So we're now going to square it to find out its typical size. So we're going to square it. The sum on j of delta wij uj. We're going to square it and we're going to average over we're going to average over I. So this equals, the square of typical size of this term. Okay, if you squared it, actually square of, it's actually, well, actually, it's probably not a good idea to write that down. So what we've done is basically squared that term. We can take the square root to get a typical size. We'll eventually take the square root. Okay. But now we can do a little bit of algebra. This is equal to 1 over k, the sum on I. The exact same thing we did before. The square of this thing is a sum on j, of delta wij nu j times the sum on j prime of delta wij j prime nu j prime. which we can write as 1 over k, the sum on I, the sum on j prime, delta wij nu j, delta wij prime, nu j prime. Now we're going to rearrange terms. The sum on j prime, nu j, nu j prime, and 1 over k, the sum on I, delta wij, delta wij prime. Okay, so what we've done is we've taken this term and put it here. We've taken this term and put it here. And we've taken the w's and put them over there. And then rearrange the sum because all the I dependence is out here. Okay. So now, this quantity here, because these delta w's are zero mean, this is 0 if j is not equal to j prime, or it's approximately 0. If j is equal to j prime, it is equal to variance of w if j equals j prime. Okay, so all the terms with j equal to j prime are 0, so they go away in the sum, and this is equal to, approximately equal to, the sum on j of nu j squared times the variance of w, right? We're just averaging the variance of w, which is equal to k, the second moment times the variance of w. Which means this term here is on the order of the square root of all this, the square root of k times the square root of nu squared bar variance of w. It's actually a Gaussian distribution, but we don't care about that. Okay, so this is super, super important. It's the same reasoning. If you add together k independent random variables, it's going to be order root k. Okay, I'm actually going to write that down again because it's critical for everything we're going to do in the next couple lectures. Okay, so let's write this down. The sum on j of wij nu j equals k nu bar w bar plus some random variable, squiggle I, the square root of k, the square root of nu squared bar variance of w. Where this actually turns out to be a zero mean unit variance Gaussian random variable. And that's from the central limit theorem. We won't really make use of the fact that it's Gaussian. Okay. So what that means is, if we go back to our equation for voltage, tau dvi dt equals minus vi minus e leak plus the sum on j. So this is time averaged of wij, let's say E nu je plus the sum on j of wij nu ji. So this term equals minus vi minus e leak plus, there's two terms, a k times w e bar nu e plus w I bar nu I. And then plus the square root of k times other terms, random variable. Okay. And what we did in our analysis so far is, so far we've ignored these terms. These terms. And that allows us to write psi nu I, say nu E equals psi E of nu E and nu I, okay? It only depended on, if we ignore these terms, and the firing rate only depends on the average firing rate of these terms. And that sounds kind of reasonable. There's one wrinkle in all this. The wrinkle in all this is that, what happened here? The wrinkle in all this is that if you look at this term, so remember Wi is negative. And these terms, and WE bar nu E plus WI bar nu I nearly cancels. Okay, but that's kind of at equilibrium. But it's kind of a detail. It just says you have to be a little bit more careful. And what happens is this term here is what gives you sort of the fact that not all neurons have the same firing rate. Okay, because if you completely threw away this term, every single neuron would have exactly the same firing rate. In reality, if you look at stick an electrode in the brain, there's a big range in the firing rates of the neurons. Okay. Okay, I'm going to take a break, but there's the thing that you guys absolutely have to absorb for the next, especially for when we talk about Hopfield networks, structured connectivity, is that there's someone.
Excuse me, Professor?
Yes.
Yeah. Since you have uploaded the Zoom recording to the website, but we cannot download them. Could you figure out another way for us to download the recording?
I'm really sorry, I screwed up. I forgot to change the permissions. I believe I've changed the permissions now. Have you checked in the last couple of days?
Maybe not only for the permission. I think maybe for the software Zoom. Yeah, since we cannot use Zoom.
Oh, you can't use Zoom.
China. Yeah, maybe this could be the reason.
Oh, I'm so sorry.
Maybe you can try Google Drive.
I will look into it. I don't know how to do that. Maybe I can put it on YouTube. That's a good point. Very sorry.
It's okay. Okay. Thank you anyway.
Yeah, I wondered what happened last year.
I don't know why. Yeah, last year, I succeeded to download the recordings. Yeah, but I don't know why.
Okay. Yeah, I will look. Maybe I'll look into that. Maybe YouTube. Maybe I'll figure it out, or try to figure it out.
Okay. Okay. Thank you.
Okay.
We can take the break now.
Well, I'm gonna write down one thing before you that I want you guys to definitely memorize. Remember. So squiggle I. So squiggle I is a random variable. So mean equals mu. We'll just call this squiggle I. Variance equals sigma squared equals squiggle I squared. And covariance equals 0 equals squiggle I, squiggle J, I not equal to j. Okay, in the sum, I equals 1, I'll put n this time, of squiggle I is approximately equal to, well, equals n mu plus the square root of n times sigma times some random variable, 0 mean random variable. And it's Gaussian if n is large. Okay, and so this, you guys really, really need to understand this because we're going to use this over and over and over. Okay, so let me take a 5-minute break. And when we come back, we'll talk about structured connectivity. And feel free to ask me any questions in the next 5 minutes.
Hello, Peter.
Hi.
I want to ask, what is about cancel at equilibrium?
Hold on a second. My video got turned off. Let's go back to
Okay.
this equation, okay? When I talk about them canceling at equilibrium, that's the question. That's the thing you're asking about.
Oh, yes.
So it turns out, and we may actually talk about this. So if you look at this term looks like it's proportional to k. And this term looks like it's proportional to root k. All right. But it turns out, for reasons that are hardly obvious, that let's do green. So k, I mean, I'll get there's some reference on the website, but it's not super important for what we have to do. So kwe bar nu e plus wi bar nu I actually proportional square root of k. And the reason is that when I say cancel, I mean we bar nu e plus wi bar, oops, plus wi bar nu I is proportional to 1 over root k. Okay, and that's not obvious. There's some write-ups that'll tell you why that's true. Got to be careful because I use a different scaling for W's. So the write-up's a little bit different. But when I mean cancel, what I really mean is this. It's this. And remember, this is negative. Sorry, I have to get to the, there we go. Wi bar is negative because the neurons are inhibitory. So what this says is the excitatory inhibitory drive nearly cancel. And again, that should not be obvious from anything I've said. That's just a fact that we won't really need, at least not for a while. Okay, makes sense? Or was that your actual question?
Oh, okay.
It's a bit of a side point, actually, for what we do.
I also want to ask the vector fields.
The vector fields.
Yeah, what will happen to the unstable point?
So let's actually look at it. I mean, so you mean what the vector fields look like near an unstable point?
Yes.
Okay, so
You will go away or
there are two kinds of unstable points. So one unstable point looks like this, where everything is going away. Okay, that's unstable. That's super unstable. There's sort of three kinds of unstable fixed points. That's very unstable. So there's also a saddle. So I'll draw some points. So these are actually the stable and unstable manifolds. And here, the vector fields go sort of in here and like this. Okay. So what this means, if you start exactly on this line, you'll end up at equilibrium. Start above it, you'll end up going up here. If you start below it, you go down here. And then there's one more kind, which is basically, this is a Hopf, where you circle around the fixed point. So you start here in the vector fields, go like that. So in this case, if you start right on the fixed point, you're fine. Start a little bit off, you circle around. And that's actually the, so this point here, point in the middle, where'd it go? Yeah, this point here might be stable. It also can be unstable via Hopf. So it's possible for that to be unstable in the you just circle around it. If that's the case, these oscillations last forever. If it's stable, you circle in and these oscillations are damped. Okay, did that answer your question?
yeah.
Okay, I mean, all this stuff is kind of, it's depending on your background. If you had sort of a class in ordinary differential equations, especially nonlinear ones, this will be fairly straightforward. If you haven't, I'm guessing this is kind of new material. So how hard this is depends a lot on your background. I put a couple homework assignments, these were homework assignments from a class I teach. And I pointed out some that if you try to work them, it should test how much, it kind of give you an idea of the kind of things. I mean, if you try to work with problems, you'll probably learn some things. Let's put it that way. Okay, let's save these things. Let me make sure they actually saved. Yep. Okay, so unfortunately, I don't know why Zoom only allows 12 of these things. Is it only 12? Yep. Zoom is irritating. So I can now talk about structured connectivity. Okay, so far we've considered random connectivity. We're going to switch to structured connectivity. Oh man, where's the eraser? Sorry, I have to wait for, there we are. Structured connectivity. Okay. So one way to think about this, remember about what apparently is my favorite equation, dvi dt equals minus v minus e leak plus the sum on j, say we ij mu ej plus a sum on j of wi ij mu ij. So we can actually do either one, but what we're going to do ultimately is take this thing and have it be random plus structured. Okay. This is our ultimate goal. Okay. We do that probably in the next lecture. But what we're going to do first, so this is our ultimate goal. So step one, structure only. So we'll have no random components at all, and very simple dynamics. And that's going to give us a Hopfield network, which was very influential, although as we'll see, turns out not to be relevant. Okay. Okay, so we're talking about the Hopfield network. It's a model for associative memory. And so I'm going to tell you sort of what problem it was trying to solve. So our memory works very different from computer memory. You can think of, some partial scene. You can see somebody wearing a red sweater and that reminds you of a person you know. You smell something, it reminds you of something in your past. And the way to think about this, so those memories correspond to neural activity. This activity space, which we draw like this. So the firing rate of neuron 1, firing rate of neuron 2, firing rate of neuron 3. So this is firing rate of neuron 1. Okay, and of course there are really millions of neurons in here. Can only draw in 3D, but let's say, so points in this space represent something. So this point might represent a dog. Let's say some memory from the past. Memory 1. So memory 1. That might be some person you know. Memory 2. Vacation you went on. And so basically, when you recall that, there's a certain pattern of activity of neurons in your brain. And to activate those memories, you don't have to specify them perfectly. It's not like in the computer where you just sort of point to a location of memory. Presuming what happens is you remember something close. So memory 1 is some person, you remember their name, and under network dynamics, you go to here, okay? And then the same thing here. I forget what this memory was. Okay. So this is under network dynamics. And by network dynamics, I really mean this, right? Memory potential evolves in time. Where it ends up depends on initial conditions. Okay. These are actually spikes, not firing rates, but it doesn't really matter. And that dynamics takes you to a fixed point. And that fixed point is a memory. So this is the person you know, this was, I forget, vacation you went on, things in your past that you remembered, okay? And we know that's from introspection, we believe that's kind of how memory works. Recall one piece of it, and so recall one piece. Piece of a memory. And get the whole thing. And that's called content addressable. I'm not sure I'm going to spell this right. Memory. Okay. Different from computer memory. Computer memory, you know, you put in a location in the machine, it goes to it. Here you put in what it is you want to recall and you go to it. Okay. You can imagine it's super, super useful. Without it, memory would not be that useful. These memories in the brain. So what we want to do is write down neural dynamics that's going to give us a bunch of fixed points. So goal write down give us fixed points. And we're going to use insanely simplified dynamics. So first step, dynamics is going to look like this. S is going to be the activity of a neuron, Si at time t plus 1. We're going to discretize time equals theta. Actually, it's not even theta, it's worse than that. Equals sine of 1 over n, the sum on j of j I j sj of t. Okay. So we've discretized time. Time is no longer continuous. It comes in steps. Okay. And because of the sign here, okay, so neurons, instead of having a continuous fire rate, neuron either fire Si equals 1 or a silence, which we take Si equals -1. We could have done 0, 1, but we do +1 and -1 just because it's easier. And then this Jij is the connectivity matrix. Okay, and what we want to do is choose a connectivity matrix so that we get lots of fixed points. And this is actually this idea of, you know, so this approach to neuroscience where here's a problem. The problem is that we can remember things using content addressable memory. We're going to make up an algorithm to do that. And then once we have the algorithm, we can check in the brain and ask if it's consistent with what the brain does. And if it is, we say, okay, we've learned something about the brain. It doesn't always work very well. Sometimes it works better than others. In this case, it kind of works. Okay. So, I put these papers online in 1982. John Hopfield made up a connectivity that actually worked really well. So Jij equals sum mu equals 1 to p of squiggle I mu squiggle j mu. And technically Jij equals 0 for I equal to j, but we're not going to really need that. That's a technical condition that's useful for some things, but we'll ignore that. Okay. It doesn't really matter. And what's squiggle I? So squiggle I, these are completely random binary vectors, equals +1 with probability 1/2. And -1 with probability. Okay. And so P is going to be, so P equals, so these completely random binary vectors. So random binary vectors. Okay. And P equals number of memories. That we're going to see that in a second. Okay. And so here's the picture. If this is our population of neurons, so population of n neurons. So we'll look at one memory. We're going to look at memory mu. So memory mu. It kind of just divides the population in half. So in this half, squiggle I mu. In this half, squiggle I mu. Okay. So any neurons in this half are excite each other, right? The squiggle I mu, if you look up here, if squiggle I mu and squiggle J mu are both positive, Jij is excitatory. So neurons in this half excite each other, E. Neurons in this half excite each other, these are also E. But if squiggle I mu and squiggle J mu, if this has +1 and this is -1, or this is -1 and that's +1, Jij is negative. So if you look across, then they inhibit each other. Okay. So neurons in this half excite each other, neurons in this half inhibit each other. So what you might expect is that an equilibrium so SI equals +1 when squiggle I mu equals 1, and SI equals -1 when squiggle I mu equals -1. Okay. And the plus and minus were kind of weird. So so this is and this would make sense, right? If you look at this, the -1s excite each other, they keep them at -1. The +1s excite each other, they keep it at +1, and they inhibit each other. So these -1 turns out into 1, and +1 turns out into -1. So the -1 is going to be a little bit weird, but we'll see that that actually makes sense. And actually, you can switch the signs if you want. You can have SI equals -1 and SI equals +1. We won't worry so much about that. Okay. So that's, but of course there are two problems. One is, this -1 is kind of weird. The other is, this is just for one memory. What about all the other memories? Okay. So we're just going to guess that this is a solution, and we're going to ask if it's consistent. Okay, so we'll go back to our equations, which look like this. So we're going to rewrite those. So SI t + 1 equals sine 1/n. Now we're going to place our Jij by the sum on mu. Actually, let's make this sum on nu of squiggle I nu squiggle J nu Sj of t. So here's our guess. SI equals squiggle I mu. It should have been what I wrote on the previous page. Oh yeah. Basically, this here is basically says SI equals squiggle I mu, right? Okay. And we're going to see if that guess is consistent with these equations. So we're going to write squiggle I mu equals, and we'll put a question mark here because we don't know if this is really going to happen, sine of 1 over n, the sum nu equals 1 to p of squiggle I nu, squiggle j nu, squiggle j mu. Okay, so we basically replace si by squiggle I mu and sj by squiggle j mu. So what we're going to do is separate out the nu equals mu terms and nu not equals. So this is equal to equals sine of 1 over n. There's a sum on j here, of course, of the sum on j of squiggle I mu, squiggle j mu, squiggle j mu. That's the nu equals mu term, and there's also plus 1 over n, the sum on j of the sum on nu not equal to mu, squiggle I nu, squiggle j nu, squiggle j mu. Okay, squiggle j mu squared is just equal to 1. The sum is from 1 to n, so this term here is just equal to squiggle I mu. So what we have is squiggle I mu equals a sine of squiggle I mu plus 1 over n, the sum on j, the sum nu not equal to mu of squiggle I nu, squiggle j nu, squiggle j mu. Okay, so if this term were 0, our guess would be correct. All right, let's put a question mark there. Because if this were 1, the sine of 1 is 1. If that were minus 1, the sine of minus 1 is 1. But how big is this term? So I'm going to write that on the next page. So squiggle I mu equals, with a question mark, sine of squiggle I mu plus 1 over n, the sum on j, the sum on nu. This is from 1 to n. 1 nu not equal to mu, so there are p minus 1 terms in that sum of squiggle I mu, squiggle I squiggle I nu, squiggle j nu, squiggle j mu. So how big is this term? Okay, so that's actually, given what I said earlier, so all these terms, so these are plus or minus 1, and they're uncorrelated. Okay, because these are completely random variables. So squiggle j mu, this term here, is plus or minus 1, independent of what these are. Even when I equals j, where this is 1, this can be either plus or minus 1. So we have 1 over n, the sum j equals 1 to n, the sum nu not equal to mu, and there are sort of p minus 1 terms in there we're going to just call this eta I j mu plus minus 1. So we have n times p minus 1 terms that are all random. So this term scales as, so this term here, oops, I don't know why that keeps happening. So this term scales as the square root of n p minus 1. Okay, that's a super, super, super important fact, which I wrote down at the very end. If you have, n, if you add up n uncorrelated random variables, it scales as root n. If you add n p minus 1 uncorrelated random variables, it scales as square root of n p minus 1. Insanely important fact. It's like flipping coins. If you flip 100 coins, it's going to be about 50 of your heads plus or minus 10. If you flip 1,000, it's about 500 heads plus or minus square root of 1,000. Okay. We also have the factor of 1 over n over here. So the whole term scales as root n p minus 1 over n equals the square root of p minus 1 over n. And for large p, that's about square root of p over n. Okay. So that means we can write squiggle I mu equals, put a question mark, sign of squiggle I mu plus some random variable, the square root of p over n times some random variable. And this turns out to be, so the zero mean unit variance. And it's also Gaussian, but we don't care about that. So what's the picture? The picture is, so here's sort of the squiggle axis. This is +1, and this is -1. And if you look at what goes inside here, it's a random variable at squiggle I month. So squiggle I mu is 1. This noise means there's some randomness around this. Oh, man. Okay. There's some randomness around here. Yeah. Gaussian random variable for different values of I. And over here. And the width of this is a square root of p over n. So as long as p over n, so if p over n is much less than 1, then squiggle I mu, then sine of squiggle I mu plus the square root of p over n, eta I, is approximately equal to squiggle I mu. Okay. If that Gaussian isn't very wide, it's exponentially unlikely for this to leak over to this side. And even if it does leak over that side for one or two values, it doesn't really matter, right? In large n limit, it's okay. So what this suggests is that, if n is large, you can still store a lot of memories. And what Sompolinsky and colleagues showed is that as long as p over n, so if p over n is less than 0.138, then SI, so So SI is approximately equal to squiggle line mu, is a solution. There's a fixed point of the dynamics. Okay. So we really do, under these dynamics, which are massively simplified, we really do have this picture. It's in discrete space, but still, if you start here, these memories now, a particular memory is going to correspond to, so memory just now means a squiggle line mu. So squiggle eye, let's say mu equals 1, and this memory is squiggle eye mu equals 2. Okay, so that's kind of cool, but a couple things are strange about this. First of all, this doesn't really look like neural dynamics. So let's write down things that we might worry about. So equations, so problems. So one, equations don't look like real neurons. Okay. Two, there's no background state. Okay. It's a case where you always have to be remembering something, which is probably not what you want. It's like getting a song in your head, stuck in your head. Once that song leaves, another song arrives. Okay, it's almost in the memory. You don't want to have that. And the third problem is that connectivity was all to all. Okay. In reality, each neuron makes a connection to another 1,000. And that turns out to be important. So this P around less than 1.38. So remember what this means is you can store, so P equals number of memories has got to be less than 0.138 times n number of neurons. Okay. And that's huge, right? You can easily have a network with 1 million neurons. That's 138,000 memories. That's plenty. Or you have 10 million neurons, 1.38 million memories. And you can even, this can be, you can even make that 0.05 or 0.01. You easily have a network with 100 million neurons. 0.01 of that is 1 million memories. So that looks like a really, really good network if we can solve these other problems. So it turns out we are going to talk about the problem with this one. So easy to, this is fixable. And I'm going to do that. The problem with this one is that each neuron makes K connections. And that implies P is proportional to not N, but K. Now, for some models, you can divide by, actually, we'll just leave it at that. Okay. Proportional K. And that actually is the biggest problem, currently unsolved. Well, there may have been some recent advances. So what we're going to do in the next lecture, so first of all, I'm going to show you that P is proportional to K if you have fixed number of connections, and then we're going to actually write down more realistic dynamics. Okay, and that'll be for Hopfield networks. Okay, so that's it. Sorry, I went a little bit over, and sorry about the technical problems in the beginning. I'll see what I can do to. I'll figure out some way to fix the Zoom link. Yeah, and I'll see you guys on Thursday. I'll stay here for about 5 minutes if there are any questions.
Hello, Peter.
Hi.
I want to ask, what is the discrete time? And is the figure change with the time?
Yeah, so the discretized time, are you talking about this?
Yeah.
Yeah, so that just basically says it's a massive approximation. So so what exactly is your question? Are you asking if it's a realistic model or why we use it? Or what is
So you mean when s is equal to 1 and we go equal to 1, then the next time is 1. Is that right?
Well, so let's actually give an example.
Oh, okay, I like an example.
Yeah, so let's say we only have 2 neurons. So n equals 2, and then at t equals 0. So S1 of 0 equals 1, and S2 of 0 equals -1. Okay. And normally we have different, for voltage, we had a differential equation. Sorry. This is going to be maybe a little long-winded, but I think it's kind of important. So we had a differential equation. Which was dvi dt equals a bunch of stuff, right? But that, if you solve that in a computer, you actually have to discretize. You would write vi of t plus dt equals vi of t plus dv dt times dt. So if you solve that on a computer, this is what you do. So basically what you would do is, this is the t-axis, this is t plus dt, t plus 2 dt, and so on. So discretization is actually really sort of in some ways how differential equations are solved. So the only difference is that time is now, instead of dt, it's 0, 1, 2. Okay. So we know SI at 0, say S of 0. So now S1 at 1 times 1, okay, is equal to sine of 1/2 J11 SI at 0 plus J12 SI at 1. And S2 of at time 1 is a sine of 1/2. The 1/2 is just because n equals 2 of J21 Si of 0 plus J22 Si of 1. Oops, also of 0. Sorry, completely wrote that wrong. J12 S2 of 0. J22 S2 of 0. Okay, so let's make up some numbers of these. 1, -1, -1, and 2. Okay, so this is equal to sine of 1/2. So 1, J11 is 1, this is a 1 here, 1 times 1. -1 times -1 is +1.
But how can we determine J?
How can we
It's
determine what?
determine the J because it contains the probability. Yeah.
Sorry, I didn't understand that word. Say it, just repeat that again.
Okay. How can we determine J?
Oh, J.
Yeah, J, because it is the probability and
So
it can be
J,
1 or
So
-1.
J is just, sorry, so let's go back to J. I see. So what happens is we choose all these random numbers. And then we basically collect all the random numbers. And so J then just becomes, oops, sorry. So J just becomes a number, right? So it's created probabilistically, but on any realization of these things, J is just a number. Okay. That makes sense. It doesn't change on every time step. So J is fixed throughout the whole process. That makes sense?
Yeah.
So let's actually take it. I mean, we can do another example where, again, we'll say S equals, so n equals 2. So we have squiggle I mu. So I equals 1 to 2, and let's say 2 memories, mu equals 2. So mu equals 1 to 2. And so these are so we'll say squiggle I mu equals, these are plus or minus, let's say 1, 1 and -1. So this is I equals 1, I equals 2, and this is squiggle I. For the first memory, squiggle I1 and squiggle I2 is equal to, let's say, 1, 1. Okay, just a bunch of random numbers that we pulled off. And so Jij is equal to squiggle I1 squiggle J1 plus squiggle I2 squiggle J2. So J11 equals, this has to equal 2, right? I equals J. So J11 equals 2. J12 equals, so this is squiggle I1, this is a -1 times a -1, and this is a 1 times 1, so this is equal to 0, equals J21, it's all symmetric, and then J22 is equal to, also equal to 2, okay? This very, very simple problem, our connectivity matrix, it just looks like that. And this is now, once you've chosen these, so once you've chosen this would fix. Okay.
Yeah. So what's the relationship between the J and the memory?
So the squiggles tell you the location of the memories. So
Oh.
remember, so basically this was our guess, right? Where's our guess? Yeah, this is our guess. The guess is that this is a fixed point of the dynamics. This is our guess. So that means, so basically S, the vector S equals a vector squiggle mu is a fixed point of the dynamics. Which means if you iterate this, if you ran this equation over and over again, you start at t equals 0 with some initial conditions close to this. Oops, why does that keep happening? With some initial conditions close to that, right? If you started with SI near squiggle I mu and ran this dynamics, it would end up at squiggle I mu. Okay, so the squiggles, which are random binary vectors, end up being the memories.
Yeah, I think maybe it would be better if we can plot all the figures and we can show how it changed with time.
Yeah, I mean, if you want, I mean, it's really easy to write a computer program. It's kind of, because the trajectories are not continuous, they're discrete. It's hard to plot them. But
Yeah.
if you wrote, I'm actually going to write down. So if you look, I gave you some homework assignments. Not, you don't have to do them, but you might want to look at them. And that gives you a continuous time Hopfield network, which is a little more, maybe a little more intuitive. Or you could write, it's really easy to write a computer program to plot this, and you can see the SI getting closer and closer to the squiggle I mu. So in fact, what you can plot is, so I'm going to talk about this the other day, there's something called the overlap. So mu equals 1 over n, the sum on, this is a function of t, sum on I of squiggle I mu SI of t. And so if you plot mu versus time, what you'll find is that if you start, this is t equals 0, and this, so you can see, so remember that mu equals 1 if SI equals squiggle I mu. Okay, because squiggle I mu squared is 1. This is sum I equals 1 to n. So if you start at t equals 0, SI of t is close to squiggle I mu, not exactly close, if some bits are switched. This is at most 1, it starts off, it could be 0, it could actually be -1. But what's going to happen if you start here, so mu will go up to here, mu, and then all the other ones will go down to 0. And I've drawn this as continuation time, but in fact, you can just get, okay. So if you want to write a program and you can plot mu and you'll see this happening. As long as there aren't too many memories.
Oh, okay. Thank you for keeping you so long.
Okay, no problem. I will.
See you next time.
Okay, see you.